What I want to do here is what's called the least squares approximation. Okay, this is maybe an idea that you've seen if you've taken a statistics class, as you want to get the regression line, right? The line of best fit based on what's called the least squares regression. But the idea of least squares is actually a linear algebra idea. And so what I want to do with that is I want to kind of describe this process. Before we do that, there's a little bit of background that we have to talk about. Um, we talked in chapter 4 about taking a matrix and then looking at the columns of that matrix, and it turns out that columns of the matrix are going to span a subspace of Rn, well, whatever the size of the matrix is. And yeah, so we talked about that. And what we can do with that is I want to think about the following. So I want to think about if I take a matrix A, and so let's say we have columns A1, A2, up to A, let's make sure I do this right. I want an M by N matrix. So I want N columns. Each of them live in Rm. So that should be fine. So if I have a matrix A like this, we can talk about the column space of A. And I think before I called it the column space of A. Right now, I'm just going to call it C of A, just for concision, just to write it a little bit nicer. Okay, so we can talk about the column space. That's just the span of the vectors in the appropriate dimension. And what I want to do is I want to think about what is the column space of A perp. In other words, what's the orthogonal complement of the column space of A? And it turns out that there's a very nice answer which will be useful for us. And rather than go through and do this abstractly, I just want to do one example. Let's pick A to be the matrix that's going to be 1, 2, 3, 4, 5, 6. Okay, and then I want to think about what is the column space of A, and then in particular, what is the orthogonal complement of the column space of A? And so the column space of A is just going to be the linear combinations of these vectors. So it's going to be A plus 2B, 3A plus 4B, 5A plus 6B, where A and B run through the real numbers. Okay, so A and B are real numbers. And so that's going to be all of the vectors that are in the column space. That's exactly what the column space is. It's just a set of linear combinations of the columns of A. And let's think about what it means to be perpendicular to that. So if I take the orthogonal complement of the column space of A, let's think about what that means. This is going to be all the vectors that are going to be orthogonal to everything in the column space of A. And remember that when we're talking about the orthogonal complement, one nice computationally slick way to do this is to compute all the vectors that are orthogonal to the basis vectors of the column space. In this case, the basis vectors of the column space are just the columns themselves. So the column space of A, the orthogonal complement of the column space of A, is going to be all of the vectors x such that, and here x will be in R3, such that x dotted with the basis vector 1, 3, 5 is 0, and x dotted with the basis vector 2, 4, 6 is 0. Okay, so all of the vectors that have both of these together at the same time, they satisfy both of these equations, that all those vectors are going to be the things that are perpendicular to the column space of A. It's the orthogonal complement of the column space. And if you actually write out what this is, say X is the matrix X1, X2, X3, or X, Y, Z, or whatever you want. If you actually write this out, what this means is that you're going to be solving, lo and behold, it's like there's only one question in all of linear algebra. You're solving a system of linear equations. You're solving X1 times 1 plus X2 times 3 plus X3 times 5. Right, I'm taking the dot product here of x and the vector 1, 3, 5. Here, the dot product, I'm just, it's a notation thing, but we're looking at column vectors. But otherwise, so you take 1 times x1, 3 times x2, 5 times x3, add them all up. This should be 0. And Likewise, 2x1 plus 4x2 plus 6x3 is 0. Okay, so we're looking for all the values that satisfy both equations at the same time. We're trying to satisfy the system. The second system, it turns out you can just divide everything by 2 because everything's even, the right side is 0. And so here the system is really x1 plus 3x2 plus 5x3 equals 0, and x1 plus 2x2 plus 3x3 equals 0. And then we could just solve this one. I mean, you could put it in a matrix, try and solve it and do it whatever way you like. But let's just subtract one from the other. You get, if you subtract the bottom from the top, you end up with the x1's canceling. You get x2 plus 2x3 is 0. So it turns out x2 is going to be negative 2x3. And once you take those values, you can plug it back into either the top or bottom equation. I think the bottom one's slightly easier. x1 is going to be negative 2x2 minus 3x3. And that's going to be, let's see, negative 2 times x2, so negative 2x3. And x3 is, oh, I'm just subtracting 3x3. So this is going to be x3. So x1 and x3 are the same. And x2 is going to be negative 2x3. And therefore, the orthogonal complement of the column space of A is just going to be all of the vectors where, let's see, so we have x1 and x3 are equal. So let's call x3 our t. So we get t and t, and then x2 is negative 2t. And here t is a real number. So this is just the span of the column vector, 1, negative 2, 1. Okay, but that's the orthogonal complement of this space. And if you actually compute negative 2, 1, negative 2, 1 dotted with 1, 3, 5, you get 0. And if you compute, 1, negative 2, 1 dotted with 2, 4, 6, you also get 0. Okay, so these really are orthogonal to each other. And so that's the orthogonal complement. Now, on the one hand, that's kind of the end of the story. But on the other hand, let's think about what's the nullity, what's the null space, I shouldn't say nullity, but what's the null space of A transpose? Let's think about what that means. So remember, the null space is going to be the set of vectors, again, just based on the fact that A is a 3 by 2 matrix. A transpose will be 2 by 3, and therefore X will be on R3, but where A transpose times X is equal to the 0 vector. Okay, so X is a 3 by 1 vector. The 0 vector here is the 0, 0. It's a 2 by 1 0 vector in R2. And A transpose is a 2 by 3 matrix because A is 3 by 2. So let's think about what this means. If I have a vector X in R3, this again I can think of as x1, x2, x3. This is going to be all of the vectors x1, x2, x3, such that A transpose, which in our case is going to be, let's take the matrix A and take the transpose. So the top row will be 1, 3, 5. The bottom row will be 2, 4, 6. And then we're going to multiply that by x1, x2, x3. And that should be the 0 vector, 0, 0. And lo and behold, look at what's going to happen here. This is all of the vectors, x1, x2, x3, all of the vectors of that form, such that, think about what happens when we do this matrix multiplication here. We have 1x1 plus 3x2 plus 5x3 equals 0. And 2x1 plus 4x2 plus 6x3 equals 0. So this is just the set of all the vectors x1, x2, x3, such that x1 plus 3x2 plus 5x3 is 0, and 2x1 plus 4x2 plus 6x3 is 0. Right? This is exactly the column space of A perp, the orthogonal complement of the column space of A. Sometimes we say, I've said this a couple times, I might as well say, we say C of A perp, meaning it's the orthogonal complement. So that turns out that these are the same in this case. And of course, there's nothing special about the matrix in general. So in general, the orthogonal complement of the column space of A is nothing more than the nullity of A transpose. Okay, so that's a very nice kind of deep fact, not too deep, but a useful fact for what we're going to do next. Okay, so that's the first thing I wanted to kind of get out here. The next thing I want to do is kind of describe what the problem is that we're going to try to solve, or what we're going to do to find the best solution here. And I'll explain what I mean by that. But here we're going to be talking about the problem of least squares. So least squares approximation. And what this means is that you're going to look at a matrix equation AX equals B. Now, typically, A is not going to be a square matrix. And therefore, you are not going to be having a unique solution, right? You get a unique solution when A is an n by n invertible square matrix. But in general here, A is going to be n by n. So what we're going to be looking at is a matrix equation here. So A is n by n, X is n by 1, B is m by 1. Okay, these dimensionality constants aren't too important, but just to keep track of them. And generally, we're going to be looking at solutions that are inconsistent. And so what we did before is we looked at solutions that were inconsistent and just said, no solution, that's the end of the story. But it turns out we can do a whole lot better. And this, again, is a very useful idea that comes up in statistics, among many other places. But when you do linear regression models and the general linear model in statistics, this uses the method of least squares. So the idea here is, even if you can't solve the system exactly, can you find the value of X that's going to be the kind of the best approximation to a solution? And so that's going to be the problem that we're going to try to solve. Okay, so we're going to try and find the value X that's going to be best here. What I mean by best is if I let E be the error, in other words, the value AX minus B, what I want to do is I want to find the value X so that E has a minimal length. So we want to talk about the minimal length of E. Here we're talking about the length of a vector. E is just going to be some vector in, it's an m by 1 vector. So this is going to be E1 squared all the way up to EM squared. And so what we want to do is we want to minimize the sums of the squares, because we're trying to minimize the length of that vector, hence the name least squares. Okay, so this is really a linear algebra thing. So the way that we're going to do this is we're going to think about this kind of in the following way. So if I look at AX equals B, so if I take AX equals B, what we're going to do is we're going to think about kind of our subspace here is the column space of A. And this is going to be, I'm just going to represent this as a flat two-dimensional plane. And our value that we're going to be looking for, okay, so our value B that we're going to be looking for is going to be some vector. So let's draw the vector in purple. It's going to be some vector, maybe it sticks up and out of the plane like that. Okay, so this is going to be some vector B. And so we are not going to be able to solve this problem exactly. But what we want to do is we want to find the vector that's in the column space of A that's kind of closest to B. And so what this is going to do is you can just take the orthogonal projection. Okay, so this is the projection of B onto the subspace C of A, right? The column space of A. And that's going to be what your answer is, basically. Okay, so your X that's going to be the closest here is going to be the projection of B onto C of A. And so you want to solve the system in that way. So that's basically the idea here. But it turns out that actually solving the system, even if you know that, so let me write this a little bit better here. So what I mean is, if I were to take AX equals the projection of B, okay, that is going to be, that's where we'll get our solution from. But there's a nice trick here. It turns out that it's still hard to figure out what is the X that gives us this equation, right? Even if we know A, even if we know the projection of B exactly, it's still tricky to figure out what's the X that's going to solve the system, because A is not square, right? And so solving this is going to involve, reducing matrices, and it's going to be a little bit complicated. And anyways, there's a trick coming. It turns out what we really want to do is we want to take this ax equals the projection of b and subtract b from it. Okay, so we're going to have ax minus b, and that's going to be equal to the projection of b minus b. Now remember that this is the thing that we're trying to minimize. And if you think about it, again, you're in an advantage if you've taken Calc 3 because you've been thinking about vectors for longer than the rest of us. But if you think about the projection minus b, what that's going to be is this projection, that's going to be the vector that you have to add to b to get the projection of b. And in other words, what this is going to be is it's going to be the vector from the tip of b down to the tip of the projection. So it's going to be this vector straight down into the orthogonal complement of the column space of A. So this is the vector that we called E. I'm going to run out of colors here, but let's make this green. Okay, so this green vector is our E. That's the ax minus b, or the projection of b minus b. It turns out that the projection of b minus b, so the projection of b on, I'm sorry, this is a projection of b on the subspace C of A, the column space of A, minus b, it's going to be orthogonal. It's in the orthogonal complement to the column space of A because it's orthogonal to. We're talking about this orthogonal projection. That's actually what this vector projection is called. It's the orthogonal projection, right? You stand exactly above the tip of the vector B, you shine a flashlight orthogonally down onto that subspace, you look at the shadow that it casts. So that's orthogonal, orthogonal projection. And so ax minus b is going to be this vector, projection of b minus b, and that's in the orthogonal complement of the column space of A, okay? Because it's orthogonal, it's sticking right down into that space. And if we think about it being in the orthogonal complement of the column space of A, what that really means is that ax minus b, which is the same thing, is in the orthogonal complement, and therefore ax minus b is going to be in the null space of A transpose, because we just said before that the orthogonal complement of the column space and the null space of the transpose are the same. Those are equal. Okay, so those are actually equal. And so what this means is that we're going to get a solution when what we do is we think about A transpose times AX minus B equals 0. We're going to get our least squares solution by finding a solution to this equation. Okay, this equation looks more complicated than the previous equation does, but I promise you this equation here, AX equals the projection, is harder. There's a nice little trick that we're going to use here when we're looking at A transpose times AX minus B. And it turns out that if the columns of A are all linearly independent, I'm not going to prove this. Proving this is a little bit beyond what I want to do in our course. But if A is a nice matrix, and what I mean by nice here precisely is that the columns of A are linearly independent, then it turns out that A transpose times A is going to be some, first of all, it's going to be square, because that's true of any matrix A. If you take A transpose times A, you're going to get a square matrix. Just think about that for a few seconds. But it turns out that in this special case where all the columns of A are linearly independent, not only is it square, but it's invertible. Okay, and so what happens here is you get A transpose times A x equals A transpose times B. And now this system, we've multiplied both sides on the left by A transpose, but this changes the problem in such a way that now this has a solution. It has a unique solution because A transpose times A is an invertible matrix. And so you can solve the solution this way by taking the inverse of A transpose times A and multiplying on the left by that inverse. And so you multiply on the left, So that means you take A transpose A inverse times A transpose times B. Okay, and so that's the idea. That's how we're going to get our solution. And again, this does not satisfy the original equation AX equals B, but it's going to give you the minimal solution here, the least squares solution. And so this is actually a really cool idea, and it's very powerful. And I want to run through a few examples because I think the examples are really where this method is going to shine for us. So what I want to do is I'm going to compute the line of best fit. This is kind of the context where it comes up for statistics, but let's look at the points 1, 1, 2, 2, and 3, 4. Okay, and so these are not all on the same line, but what I want to do is I want to find the line that's the best fit. Okay, so I want to find the what's called the line of best fit. Okay, and so the idea here is I'm going to find the line y equals mx plus b that's going to be the best fit here. And so I want to find, actually M and B are bad choices. Let me call it C and D. Okay, I'll explain why in a second. But what I want to do is I want to look at, basically I'm going to plug in the 3 points that we have. So we have the points 1, 1, 2, 2, and 3, 4. So if I plug in 1, 1, what happens is I get 1 is equal to C plus D. If I plug in the point 2, 2, we get that 2 is equal to 2C plus D. And if I plug in 3, 4, we get that 4 is equal to 3C plus D. Now, clearly there's no solution to the system. This is an inconsistent system. But what I can do is I can take these equations, and I'm going to think of the right side here is our A times X. This is our A is 1, 1, 2, 1, 3, 1. Our X is going to be the vector CD. And then our B, I didn't want to use B before because AX equals B already has a B in it. But our vector B is going to be 1, 2, 4. Okay, so here's our A, here's our X, here's our B. And again, there's no solution, but what we can do is we can multiply on the left by A transpose. Okay, so we're going to look at A transpose times AX equals A transpose times B. And then that has a solution that'll give us our least squares solution. So let's do that. And I want to actually do this one by hand because the size of the matrices are pretty small, and it's a pretty cool, pretty powerful thing here. Clearly you can type this into a, some sort of like programming thing like MATLAB or what's the other one? Maple, Mathematica, that's what I'm thinking of. And you can type it in and, that'll spit it out, the answer for you. But I think it's really nice just to see how this works by hand. And so if I take A transpose times A, let's compute that first. So A transpose times A is going to be, let's see, that's going to be 1, 2, 3, 1, 1, 1 times 1, 1, 2, 1, 3, 1. Okay, so here we're going to get a 2 by 3 matrix. So this is going to be 1 plus 4 plus 9. 1 plus 2 plus 3, 1 plus 2 plus 3, and 1, 1, 1 will be 6. A transpose times A, by the way, is always going to be a symmetric matrix because when you take the transpose, based on all the properties that we've talked about, you get itself. So this is A transpose times A. We might as well over here also compute A transpose times B. So this is 1, 2, 3, 1, 1, 1 times 1, 2, 4. This is going to be a 2 vector. So we get 1 plus 4 plus 12. So it's 17. And 1 plus 2 plus 4 is 7. Okay. And so A transpose times B is that 17, 7. And so now we're going to look at, so to get the least squares approximation, we're going to look at solving 14, 6, 6, 3 times our X, or CD, is equal to A transpose times B, which is 17, 7. Okay, and so now all we have to do is multiply on the left by the inverse, and so we can do that. Let's let M be the inverse 14, 6, 6, 3. And let's see, the determinant of m is going to be 42 minus 36, so 6. And so the inverse is going to be 1/6 times, let's see, we switch the 3 and the 14. We make the 6's negative. And so we end up with 1/2, -1, -1, and then 14 over 6 is 7/3. And then finally, this means that CD is going to be equal to the inverse, which we just said is 1/2, -1, -1, 7/3 times 17/7. So this is going to turn out to be, so our C and our D is going to turn out to be 17/2 minus 7. So let's see, 17/2 minus 7 is 17/2 minus 14/2, so that's 3/2. And then -17 plus 21, -17 plus 49/3. -17 is -51/3, plus 49/3 will be -2/3. And so that means that our line of best fit, our CX plus D that's going to work, is going to be 3/2 x minus 2/3. And so what I want to do now is I want to look at an example here. So I'm going to stop sharing and let's look at an actual example here. So here I have the 3 points, 1, 1, 2, 2, and 3, 4. And if I look at this line, 3/2 x minus 2/3, that's a pretty good fit. That's going to be the line of best fit there. Okay, so that's, I think, a pretty cool demonstration there of how this works in general. I want to do one more example, though. So the last example I want to do, this doesn't just work for lines. Let's find the quadratic best fit. This is also something that comes up a lot. And let's look at the points 0, 2, 1, 1, 2, 2, and 3, 4. Okay, so let's look at those points. And what I want to do, any 3 points uniquely determine, as long as the 3 points are not in a line, any 3 points uniquely determine a quadratic. And here I have 4 points just to make sure that they don't all fit on a quadratic. But we have 0, 2, 1, 1, 2, 2, and 3, 4. Okay, something like that. So you can get a polynomial, if you can get a polynomial that goes through any 3 of them, but it's going to miss the 4th one. That was a terrible parabola, but I can live with it. And so I want to find y equals, I'm going to call it alpha x squared plus beta x plus gamma. I want to find the values that approximate this the best. So I'll do the same thing. I'll plug in our x values and our y values. So we get 2 is equal to 0x squared plus 0x, 0 alpha plus 0 beta plus gamma. We're going to get 1 is equal to, let's see, if I plug in the x equals 1, I'm going to get alpha plus beta plus gamma. We're going to get 2 is equal to 4 alpha plus 2 beta plus gamma. And 4 is equal to 9 alpha plus 3 beta plus gamma. And there's going to be no solution to this system, but it turns out we can find the best fit here, the least squares approximation. And so we're going to look at solving. I'm going to think of this gamma as 0 alpha plus 0 beta. So we're going to look at 0, 0, 1, 1, 1, 1, 4, 2, 1, and 9, 3, 1. That's going to be our A. We're going to be looking for our alpha, beta, and gamma. And then we want this to be equal to 2, 1, 2, 4. Okay, and so this is our A, our X, and our B. And again, there's no solution. It's inconsistent, but you can find the least squares approximation. And if you take the transpose of A, multiply both sides by it, you get a 3 by 3 matrix. And then you can invert that, find your alpha, beta, and gamma. So I'll let you kind of leave the details, whether you want to just kind of implement this in a program or whether you want to actually do this out. That's up to you. But it turns out that what you're going to get is alpha is going to be 3/4. Beta is going to be 31 over 20. Let me make sure I have the numbers right. It should be negative. We'll look in a second. I have it somewhere. Beta, I think, is going to be negative 31 over 20. Yeah, negative 31 over 20. And gamma is 39 over 20. Okay, and so this is going to be the quadratic that's going to be the best fit there. So let's go back and let's look at Desmos one more time. Okay, so let's do, let's look at our points here. So I've taken these points and now I'm going to get rid of our line of best fit for those 3 points. I'm going to add in this point 0, 2. So now we have this new red point here. And the parabola that's going to give us the least squares approximation will be exactly this. So 3/4 x squared minus 31 over 20x plus 39 over 20. And so that's pretty cool, right? That's a pretty good approximation of a parabola to those points if we want to minimize the least squares there. Okay, so we're minimizing that vertical distance squared. I would encourage you to go through and to try to find the line of best fit for these 4 points. So if you go back and kind of extrapolate on the problem that we did, try and find the line of best fit, it turns out what you'll get is 0.7x plus 1.2. But I think that's a good exercise for you to try. So go ahead and try that on your own at this point. Okay, but this is the method of least squares approximation, useful in all sorts of things. So this is very useful if you have a few data points and then you want to kind of make an educated guess about how things should behave at, say, 2.5, right? So this is used for a lot of statistical inference, things like that. Okay, so this is least squares.